Yesterday, it was like very quick introduction to string theory and quantum gravity. And there's a long, long way to go to giant gravity. So let's see if I can make it. And so there are two parts apparently, giant and gravitons. Gravitons give me the equation. Okay, I'll give you H mu nu. The graviton has to come from metric, yes? Yeah, it's a fluctuation of metric. So if metric fluctuates, then what happens? Space-time fluctuates, no? Because it changes the curvature. So that's why there's gravitational waves. Yeah? Okay, but this has too many degrees of freedom. In 4 dimensions, what's the number of components? 60? 10. Yes. It's a 4 dimension and it's a symmetric tensor. So it's 4 times 5 divided by 2. But what's the actual degrees of freedom of graviton? What's the number? What's the number? Okay? What's this?
Let's spin to
what's the number? Give me the 3? Okay, no. It's too many. So it will be 6. So 3 is too many. So it's either 0, 1, 2. But just degrees of freedom, so it has to be 1 or 2. 2. Yes. 2. So this, I'm not gonna go through all these things. But first, it has to be transverse. Yeah? It's the same as photon. Yeah? So it's orthogonal to the direction of momentum. And another thing is it has to be traceless. So there are constraints. Although this will give you still 5, but there's some gauge redundancy I have to eliminate. But let's say, so gravitons, it's a metric, but it has to be transverse and traceless. Yes, okay. And giant. This is the part I have to explain today. Although still it's preliminary to giant gravitons. So you know that so this is it's giant because it's big because you should know. You are not really actually. Well, it's graviton. So as you will find, it's moving at the speed of light. It has energy. Yeah, that you know. But it's big because it's deep radius. It's like a membrane thing. So it's a deep range. So it's D3 range. And the shape is 3 sphere. Yeah, so it's gigantic because it's an object with some size, with radius. Yes.
Why is it 2 degrees of freedom?
For gravitons. So you have 10 here, and then you have 4 constraints, and you have 1. So far what you got is 5, but there's a redundancy. If you do coordinate transformation, let's say, so So then this will transform and if you carefully count, so this gauge redundancy has 3 degrees of freedom. So that's unphysical. So we have to subtract from here. So we have to subtract 3. And so you end up with 2. Another way to count is, let's see. There's another way. If you know the constraint quantum mechanical system, then you count the number of constraints in this system. Then, so what will happen is you have first, your gauge degrees of freedom is 4 because you have 4 coordinate transformations. Then to fix it, you have to impose 4 constraints. So that will give you 4 plus 4 constraints. So 10 minus 8 and it gives you 2.
I guess you could also argue using helicity, like from a physical perspective. That a massless particle can only have 2 helicities.
Yes, so that's a consequence, though.
That's a consequence, yeah, but just, yeah.
Yes. More intuitively, yes. So today, I want to explain this part. So deep brains. And what is important, there's an important concept which you may know, probe approximation. These are the things I want to explain today. Yes. So if I really try to explain deep brains, I have to go through all the supersymmetric algebra, etc. But I skip all of this and go straight to more intuitive explanation. Okay, first, so I consider superstrings. So int and d. You don't have to know the precise definition of what it is, and people actually don't know what exactly string theory is, even at the forefront of research. That's the question we have been asking. But anyway, I focus on massless spectrum. I just focus on massless spectrum of string theory. String, when it vibrates, the lowest mode is the massless one. And then as it vibrates more, then it becomes massive. But I work on the low energy limit. And you know what the massless spectrum, yes? For example, what do you have? Yes, you have gravitons, yes, yes. Dilaton, yes. Yes, dilaton.
Also,
mu, yes. So this is anti-symmetric, yeah? Yes. Okay, so bosonic string. Yes, you have this plus tachyon. So there's a T, tachyon. For bosonic string. Yes, so dilaton is a scalar field, and you know how to quantize scalar field. Yes. And G mu nu, you know from general relativity, but it's hard to quantize, as I said yesterday. And B mu nu, it's a new thing. But as I will explain, B mu nu has to be there in string theory. Okay? And so this is bosonic. And let's say superstring. Now I want to consider superstrings. There are type 2A and type 2B and heterotic string. But giant graviton appears in this type 2B. So let me start with type 2B. So it doesn't have tachyon, superstring. Superstring eliminates tachyon. Tachyon is like a Higgs particle, but it's more destructive than the so type 2B, in addition to these three, what do you have? Maybe you know the answer. Well, Robert students should know the answer because he was working on type 2B supergravity. No? So it's a type 2B chiral. This is a chiral theory. And let me forget about fermions. Okay, bosons. What bosons do they have?
So they have
six bosonic fields in here. Okay, how many? It's actually three. Right. Yeah, that's true. So give me three. And so you have three already there.
Okay.
So another three.
Then there is yeah, and then you have a gauge and quantity.
Gauge field. There's a kind of gauge field, but it's not vector. Okay. Okay. First, before going there, first you have axiom, a pseudoscalar. Yes. So then the thing you tried to mention was C mu nu. This is another antisymmetric tensor. And then you have four form. So antisymmetric rank 4 tensor. Let's say this is 4 form. So this is 2 form, 4 form. Okay, I skipped type 2A for the moment because yeah, I might not have time. Okay, so now we focus on well, this is also important, but let me focus on this and this and this. Okay, so here you make. I want to make an analogy. So let's consider electromagnetism. So in electromagnetism, you have charged particles. Yes. So, but why do they exist? And what is the characteristic of charged particles? So, if there are charged particles, there has to exist something else. Gauge field. Yes, great. Okay, so. So this charge, the fact that it has charge, it's charged under something which is gauge field. Yes. So you have gauge fields. I call it one form or gauge field. And then, so how do you see? So the way it is charged is determined by how this couples to this gauge field. Yes. And so because it's a Maxwell theory, so it's Maxwell theory. You have the action for the Maxwell theory. I should put minus in my equation. So then, here is my question: is what do you have here? Let me write charge Q. Fermionic term. Okay, let me forget about fermions. So that's not what I'm asking. So here you have to have coupling to gauge field. Yeah.
Okay, you need charge times the 1 form.
Yes, that's right. So this case. You have current and you have gauge field, no? And this, tau. This tau parameterized. Yes, the word line. Yes. So charged particle. The trajectory is a one line. So tau is parameterizing this. Yes. Good. And so if you have two charges, then what will happen is they will be exchanging gauge field. Yes. Yes, and the D planes are very in this specific context, because there could be more different kinds of D planes, but in this context, so D planes. It's a generalization of charged particles. In electromagnetic. So let's see. Okay, so in electromagnetism, you have point particle. And you have gauge field. Type 2b. Okay, first you have this C mu nu. So then my question, what could be here? So there's something charged under C mu nu. And it's not going to be a point. And it could be
like two-dimensional space.
right. Yes, exactly. So it should be. So this is called D1 plane. So it has one sheet. Similar. It's very similar to string. So it's a 1 plus 1 dimensional object. Because so in analogy to this thing, so there's this coupling, and let's call this is the one charge. Then you have two-dimensional space, and you have tensor current, and you have this coupling. Yeah. Okay. So now, yes, it was so now you have time, and space sigma. And so this is the UR plane. So you replace this world line by a world sheet. And then this is exchanging C mu nu. Yes? Makes sense. So they are interacting, and what is mediating interaction is these two forms, C mu nu. And also, because this is a gravitational theory, and these have mass, and then there are also G mu nu. Yeah? So it's they are also exchanging gravitons and also dilatons. It couples to dilaton, and so so the force caused by the exchange of two forms is that the repulsive or attractive. If you have like charges and exchanging photons, the force between them will be repulsive. Yes? So likewise, the force caused by these two forms is repulsive. But the gravity, on the other hand, is always attractive. Yes? And so is dilaton. I will not go through it. So in this case, actually they cancel. So there's no total net force acting. Okay, that's a side remark. But then you get the idea. So more generally, if you have, let's say, P form, a P plus 1 form, then the object here is the P brane, and it's a P plus 1D, one-dimensional object. Let's say this includes type 2B, type 2A. So let me ask you. So if you have this 4 form, means you have 4 legs, then the D plane you have is which D plane? Is D plane, yes. So giant gravitons, they couple to this one. So this is one thing. So this is called Ramon B. Ramon. For history and technical reason, this is called Ramon things. And this is called Witwatersrand. Okay. So this is about D brane. So D brane coupled to this and charged under this. This is one thing. Yes.
I just wanted to know, in the D brane and D1 brane picture,
Yes.
you mentioned that the gravitational force is cancelled by the force mediated by the
Two forms. Yes.
Is that always true independent of distances?
No, it's not always the case. So that's a very special case, and that's what people call BPS. Okay. And so there are many non-BPS states, meaning that there are actually forces between them. Yes. And so B mu nu. So you always actually, so the Robert always consider BPS. Yes. He must have said BPS so many times. No? B mu nu. So there's something there's some object coupling to B mu nu. Can you guess what it is? Yes, it's very similar to this one. So there's an object exchanging B mu nu. And the dimension of that object has to be four? Free form. No. So, okay, so it's two form, yes? And B mu nu is also two form. And then the dimension of this object should be? Yeah, 2, 1 plus 1. So it has one-dimensional object and moving, yes? And you have that object in string theory, yeah? 1 plus 1 dimensional thing. What is it? String itself, yes. So the string couples to this, actually. And so in this case, we call it fundamental one plane sometimes. So to distinguish this D1, the string you have is sometimes called fundamental string. So F1 plane. And so there's a bit more structure. So this is where, for example, D1 plane, this is where D1 plane differ from this fundamental string. So here's DP plane. And this is something you might know. So what structure does it have? I haven't talked about one important thing. What am I missing? Okay? Yes, good, yes. So D plane, this is an object where open strings can end. So you have open strings like this, and if you have more, then there are open strings connecting them. Yes? So this adds some more structure. Yeah? So apparently you have more degrees of freedom because of this open string ending on it. And what do you have? So you study super-Amperes, yeah. Super-Amperes comes from where? Brains, yes. Super-Amperes comes from brains. It's a low-energy effective theory of these three brains. Okay. So then it has to have. You have super-Amperes. To have super-Amperes, what degrees of freedom do you have? Yeah? Yes, Stefan. Gauge fields, yes. You have to have this. So this comes from this open string, massless excitation of open string. And also you have scalar fields. This also comes from open strings. So that's the additional structure. So D brain can be described by super ion fields. Okay. So now, good. So now, so I mentioned this to move on to the next step. So the next topic is the probe approximation I mentioned. Yes.
Is that on the endpoint
No, that's open string itself. Endpoints, you have charges. Like, so this is, for example, you have UN, super ion bells. Yeah. So then these fields are charged under UN. So charge comes from here. But this itself is the first excitation of this open string. And so is this one. And A mu is in this direction. Yeah, that's along the brane or longitudinal. And phi is this. So this excitation phi represents the transverse motion of the brane. So now I want to consider this probe approximation. This is about. This is also about. So it's a low energy. Theory. So to study this probe approximation, I need a tool, and which is the low energy effective theory of deep branes. And so let's say, so it's approximation. Let's say the first, let me strength of gravity. So because D blade, it's a massive object, and it's a gravitational theory. So then this will curve the space-time. Yes, if you have a gigantic massive object, then it's very big. It's going to be black hole. And something similar happens. But so let's evaluate the gravitational strength of D branes. So it has to be, it's now type 2B superstring, 10 dimensional Newton constant, times mass of the DP planes. Yes. Yeah, because you have Einstein's equation. Is that H5 GT? Yeah. And so G times, and the mass comes from here. Yeah? So this is the strength of gravity. And sorry. You can estimate the strength. So GS, string coupling constant. String coupling. Okay, the string has a coupling, which is GS, and Newton constant is GS squared. And the mass of D branes turns out to be 1 over Gs. So it's Gs, that's the order. And at weak couplings, if Gs is really, really small, then this gravitational strength is very small. That's when you can approximate D-planes, meaning that if you really try to analyze D-planes, you actually have to consider the effect of the curved spacetime, because it makes the spacetime curved. But at weak couplings, because the gravitational strength of D-plane is very weak, so you don't have to consider the effect of D-planes on the spacetime. So there's some spacetime, and you throw in D-plane, and then you can analyze D-plane in this fixed spacetime. So that's the proper approximation. But if you have many of them, like UN, you have n discrete branes, and if n is really large, then there will be this effect of n, yes? So if this is large, you have to consider the back reaction of D branes, or that's curved spacetime. But I consider only a few of D branes, and that's the proper approximation. So this is what we quite often. This is what we use quite often, proper approximation. Okay. Right. So then, as a concept, it's okay. Proper approximation, but so with this approximation, what can you do? So what you actually study is the following. Let me start. So that's where this low energy effective theory comes in. Yes. So again, so as a preliminary, electromagnetism. It's always good to make an analogy to electromagnetism. So I start with this. So in electromagnetism, you throw in a charge into space-time, and then you study the motion of charges. Yes? That's the proper approximation. So you have some fixed electromagnetic field, and then you consider the motion of charged particles. That's the proper approximation you consider here too. And so the action of electromagnetism has a background part plus flow action. So it has this structure. So this is nothing but this is the action for the Maxwell theory. That's the background, because that's the background field. Okay, so now, yes, probe action. I gave a part of it, I don't know, 10 minutes, 15 minutes ago. So the probe action. What is the probe action for this one? Just a charged particle in the background of electromagnetic field. Yes, so there's there's some part, and let me sign. The convention seems to be minus q. Let's say I can write like this. Yeah? I slightly changed the notation, but it's fine. And there's another part. That's something you should know because you calculated something a few years ago. Yes.
So we integrate now the ds.
Yes, exactly. Yes. So minus ds plus ds. Yes, so and the ds is this thing d tau minus g mu nu dx mu d tau. This is the thing. If you want to find, for example, the geodesic in space-time, and also, yes, so relativistic particle has this action. Yeah. So it has these two parts, and yes. So now the idea is to generalize this to the p branes. Yeah? So for the p branes, this background part, this is type 2b supergravity, type 2 supergravity. So your background action would be type 2b or a supergravity. But you don't have to worry about it. So in the probe approximation, so I forgot to say, in the probe approximation, the action you analyze is this one, yes? So you minimize this action. Minimize this. That's all you do in the probe approximation. And so this yeah, okay, so this part, so this MDS part, and you have this huge A mu dx mu part. So when you go to the p branes, first, this part will be replaced by what we call dBi action. This part, so Dirac Born inferred action. And this part, Chan-Simons action, or sometimes people call it Best-Lumino. I use Chan-Simons in this lecture. It's just the way people call it. Right. Right. So now I want to just show you what they are, and then I want to give you exercise. So first, let's parameterize the world volume of the deep brain by sigma A. So sigma A is world volume coordinates. So A comes from P, and so it's the deep brain. And so you have gauge field A mu, and you have this scalar. This depends on sigma. So you have 2 degrees of freedom. So, sorry, A, maybe I should have A. Yeah, A, sigma. Gauge fields. Gauge field on plane. And this is scalar field. On brains. And this phi, as I mentioned here, this represents the motion of deep brains in this transverse direction. So it's a motion of deep brains in the transverse direction. So what I am alluding to is, so this phi in analogy to electromagnetism, what this corresponds to in electromagnetism? Potential. No. No. This electric field, no. That would be, okay, it's important to make this show. Okay, so this corresponds to this xi, because it's the motion. And A, yes, this is a tricky question. No, yes, I thought you would say that, but there's nothing corresponding to it. Okay. And then what this A corresponds to in this here, I haven't written anything here. So that A mu, so this is electromagnetism, this is electromagnetism. And here, what are they? This is supposed to be a background field, yes? So the background fields you have for DP brains. Anything?
Before.
C. Yes, good. So C. So first, the P plus 1 form. Yes, that's the background. So that's the field directly corresponding to this mu. But there are other things. it's a gravity, yeah? Eh? What? Gravitons, yes. Yes. You have G mu. What else? Dilaton, yes. Yeah, you have dilaton. Yes. And? Okay, B. So it gets more complicated. In electromagnetism, you have only gauge field, but so that's the background. But in supergravity or superstring, you have all these whole bunch of background fields. Okay. So the action. So this dBi and Chern-Simons action becomes a bit more complicated, as you can imagine. Then here's the answer. E to the minus 5. Yes, this is the action. Yeah. This is a dBi action. So first, it's an integral over p plus 1 dimensional world volume. Yes. So this is just a world volume. So the way it couples to dilaton is this way. Well, you shouldn't ask me why. But there's an explanation, but yeah, that's how it is. And TP would be tension. Yes, tension. So having tension means the brain wants to do what? If there's a tension, brain wants to. Like a string, yeah, has tension. String wants to, shrink. Yeah, it collapses. That's the tendency. Okay, so this thing is similar to this thing, no? G dx. Yeah, so it's a generalization, but I have to explain what. So P, this is called fullback. So this is GAB and GIA del A5 I and GIB del B phi I plus GIJ del A phi I del B phi J. Okay. So this part is direct. Well, actually, this whole thing is very similar to this one. Okay, let me introduce x mu, which is sigma 0 and sigma b, and phi, let's say, p plus 2, phi 10. So nice way to make correspondence between this and this is you introduce some coordinate x, which is corresponding to this, but take the first p plus 1 component to be the world volume coordinate. Yeah. So here too, you have so here too you have x mu, and then you set this to be tau. Yeah. So then you have x1, 2, 3. So that's what it is. And you have B, and you have also the gauge field on the frame. This is how it is. So this determinant is, so this thing is p plus 1 times p plus 1 matrix. So it's the determinant of that matrix because it has indices A and B here. Okay, G, 5 minutes?
Sure.
So now I have to give Chern-Simons action. And okay, the Chern-Simons action. So you first so this is a generalization of this A mu J mu coupling here. Okay, so this is given by mu P. Okay, and the integral over world volume. So in electromagnetism case, you have A mu, dx mu, x mu. This was, so this A mu dx mu was the integral of one form over the world line. So similarly, you should have this one. So p plus 1 form integrated over p plus 1 dimensional world volume. But it doesn't stop there. So there are some additional things. Because, I forgot. So you actually have like p minus 1 form and continuous. So if you have all these forms, p minus 1, p plus 2 pi alpha prime f, and p minus 3, and p plus 2 pi alpha prime f squared, and so on. In reality, you don't have this many. So this three-plane case, you have 4 forms and 2 forms. So for these 3 planes, you have C4 and C2. That's all. So you stop there. Yes, so this is the, generalization of this coupling. Yeah? You see that it's a generalization. And because of these additional fields, it gets more structure. Right. So then you will have TAT in the afternoon. And I'll give you the problem later. Okay, so but for now, I think I should stop.